Let us today discuss about Euler Totient function. Euler Totient function, which is also known as Euler's Phi function and is popularly represented by the Greek letter phi, and Phi n represents the number of positive integers less than equal to the natural number n and co-prime to it. When I say co-prime or relatively prime, both are same things. Two numbers are co-prime or relatively primes if their GCD is 1, or in other words, there are no common factors other than 1 to both these numbers. So if you see the smallest natural number, I'm trying to see what is the phi of 1. 1 is the smallest natural number, and I'm saying the number of positive integers less than equal to n which are co-prime to n. So 1 is the smallest natural number, so obviously 1 would be co-prime to itself, and that's the only number, so phi of 1 will be 1. What is phi of 2? Phi of 2, so all the numbers which are less than 2 are 1 and 2. So 1 is obviously co-prime to 2, however 2 is not co-prime to 2 by the basic definition of relatively prime numbers. So phi of 2 as well is 1. Now let me take a slightly bigger number. Let's talk about phi of 10. So what is phi of 10? Let's count it in our fingers, starting from 1. 1 is co-prime to 10, 2 is not, 3 is, 4 is not, 5 is not, 6 is not, 7 is, 8 is not, 9 is, and 10 is not. So we observe here that there are 4 numbers less than equal to 10 which are relatively prime to 10. So these are 4 in number. Okay, now it's important to notice that if n is greater than 2, phi of n will be even. This is important. If n is greater than 2, the phi of n will be even. Why? So to answer that, let's understand and get back to our old powerful algo which we discussed a few videos earlier, which was the Euclid's algorithm. So let me say that I am finding a number which is co-prime to n. Let's say that number is a. Let's say that a is co-prime to n, and in that case GCD of both should be 1. So as per Euclid's algorithm, if n is greater than a, this must also imply that GCD of n minus a comma n should as well be equal to 1, right? If GCD of a comma n is 1, so by Euclid's algorithm GCD of n minus a comma n should also be equal to 1. And if that is the case, it establishes here that integers which are co-prime to n occur in pairs. So integers which are co-prime to n, here when I say co-primes to n, one is of the form a and the other is of the form n minus a. So integers co-prime to n occur in pairs of type a and n minus a. That's why phi of n is even for n greater than 2. Now what happens for n equal to 2 and n equal to 1? In that case, the Totient function's value remains 1 in both the cases, as we found out here that phi of 1 and phi of 2 are always 1. So 1 and 2 are the only natural numbers for which the totient function value will be odd. For all the values of n greater than 2, the phi of n will always exist in pairs such that sum of those numbers in the pair always gives the number n itself. We also saw this, before with the help of an example of, let's say, 28. I'm seeing all the coprimes of 28. What are all the coprimes of 28 less than equal to it? 1, 3, 5, 9, 11, 13, 15, 17, so on and so forth up to 27. So if you see this coprime and this coprime, if you add them, they both give 28. If you add the second with the second last is 25. So if you add 3 and 25, they give me 28, so on and so forth. So for 28, all the coprimes which exist in pair always can be paired up such that their sum is the number itself, 28. So this is why phi of n is even and always exists in pairs such that sum of the pair is always equal to n. So remember, this is a very key understanding of the totient function. Now let's look at a general expression of phi of n, which is given by phi of n. Till now we were deducing one by one by counting on our fingers phi of 1, 2 and 10. Now let's try and write the general expression for phi of n, where n is any natural number. Now we know that any natural number is formed by the decomposition of prime numbers, prime factors. So any number n is generally represented in the form of product of prime factors as n is equal to p1 to the power a into p2 to the power b into p3 to the power c into so on and so forth, where p1, p2, p3 and so on and so forth are the prime numbers. So phi of n is given by, let me write this formula here, generic formula for n, and then we'll look at deducing this formula. So phi of n for any generic n is given by n, the natural number itself, into 1 minus reciprocal of the first prime number, into 1 minus reciprocal of the second prime number, into 1 minus reciprocal of the third prime number, so on and so forth. So before deducing this expression, let me just plug in the value of for n equal to 10 and see if this value matches the one that we found out earlier. So if I put phi is equal to 10, n is equal to 10 here, I have phi of 10 equal to 10 into 1 minus reciprocal of 2 into 1 minus reciprocal of 5. So 2 and 5 are the only prime numbers, so we'll stop here. So this is nothing but 10 into half into 4 by 5, which is nothing but 4. So this calculated value matches our observed value. Now let's look at reducing the expression for phi of n for generic n. So let me create some space. Great. So I'm trying to deduce the expression for phi of n here. Let me start it like this. I am trying to find the number of integers from 1 to p to the power a. Let me have a natural number of the form p to the power a, which is only composed of the powers of one type of prime number, p only. So I'm looking at all the number of integers from 1 to p to the power a which are not coprime to p to the power a. Not coprime to p to the power a. When I say not coprime to p to the power a, understand that p to the power a is only formed by one prime number, which is p. So if my number is not to be coprime to p to the power a, understand that it must contain a multiple of the prime number p. So if I say a number must contain a prime factor p, so a number, the smallest number would be 1 into p. 1 into p would be the smallest number which will not be co-prime to p to the power a, right? So, and what will be the next number? It will obviously be the next multiple of p. So 2 into p, so on and so forth. And which will be my largest number less than equal to p to the power a, which will not be co-prime to p to the power a? The number itself, obviously. And what is that? It is p to the, it can be written as p to the power a minus 1 into p, right? So if you see, essentially we are talking about from 1 into p to p to the power a minus 1 into p. How many numbers are there? How many integers are there? These are p to the power a minus 1 in number. So we have deduced here that in total there are p to the power a minus 1 integers or natural numbers which are not co-prime to p to the power a, if we say that they are less than equal to p to the power a. Now I am trying to express what is phi of p to the power a. What is phi of p to the power a? Phi of p to the power is the number of co-primes less than equal to p to the power a and of p to the power a. So total number is p to the power a. If I subtract from this the total number of numbers which are not co-prime to p to the power a, which we already deduced as p to the power a minus 1. So this will give me the total number of co-primes of p to the power a which are less than equal to p to the power a, right? So if I take p to the power a outside, this is 1 minus 1 by p. So this is our first deduction. Second thing is, always remember, let me take an example first. Whenever you take a number like say 10, and I'm trying to say phi of 10, it's nothing but what are all the prime factors of 10? 2 and 5. So phi of 2, if I try to find out the phi of 2 and phi of 5 separately and multiply them, that's the same as phi of 10. What's the case if I take phi of, let's say 15, or let's say 12, phi of 12? It's the same as finding of phi of 3 into phi of 4. Now understand here that whenever I am able to express a natural number n into product of relatively prime numbers, 2 and 5 are relatively prime to each other, 3 and 4 are relatively prime to each other, then we can always write phi of n as the product of individual phi's of those relatively prime numbers. However, if I consider a number like, let's say, phi of 9, which has only one prime number, which is of the form phi of 3 square, I cannot write it as phi of 3 into phi of 3. This is wrong. This is not correct. Only when because 3 and 3 are not relatively prime to each other. Only when the two numbers can be expressed as relatively prime to each other, I can break down them into product of individual phi's. So important observation from here says that if two numbers whose GCD is, let's say, two number m and n whose GCD is 1, I can always say that phi of mn is equal to phi of m into phi of n. So this is my second deduction, right? Remember this, you can relate to it, you can take basic examples and relate to it. So understand that if two numbers are relatively prime, then the product of these two number, the phi of the product of these two number must be the product of individual phi's of those numbers. So if I now talk about expressing phi, now I am going to write the general expression for, let me write it here. I am now going to write the general expression for phi of n. My n, as we have already seen, is can be expressed as product of primes, so it can be written as phi of p1 to the power a into p2 to the power b, and so on and so forth. Now, if you see, the first term is entirely composed of one type of prime number p1, the other next term is entirely composed of another type of prime number p2 and its powers, and so is the case with any subsequent term in this expression. So note that every term is relatively prime to the other term, right? The first term, second term, third term, fourth term, any term are relatively primes to each other. So as established here, I can always open this phi and distribute across the individual terms and take the product. So I can write it as phi of p1 to the power a into phi of p2 to the power b, and so on and so forth. Now I already know that what is my phi of p to the power a. From here it is p1 to the power a into 1 minus p1 into p2 to the power b into 1 minus 1 by p2, so on and so forth. And if I bring this together, p1 to the power a, p2 to the power b together, it's nothing but my n itself, and I'm left with 1 minus reciprocal of the first prime number into reciprocal of the 1 minus reciprocal of the second prime number, and so on and so forth. And this is what we were looking to prove. Phi of n finally we get as n, the natural number n itself, into 1 minus reciprocal of the first prime number into 1 minus reciprocal of the second prime number, and so on and so forth. So here we have deduced by using the basic definition of the Totient function what's the general expression of phi n. Now these numbers which are relatively prime or co-prime to a given number and less than equal to it are also called totatives. These are also called totatives. So it's as good as saying what is the number of totatives of a number n. Phi n is nothing but the number of totatives of a natural number n. So now to use this, our basic understanding and significance of phi n is clear, that we are talking about all the coprimes less than equal to a number and coprime to it. Now let's try and see through very simple couple of questions how we can utilize this important number. It is a very, as we have already seen, it is a very strong correlation with prime numbers, and we can see how this phi can be applied in other type of problems, and you will then appreciate the significance of phi. So let me take one or two simple questions. So I'll make some space. So let's say I start with finding, I have to find all the integers or natural numbers, positive integers or natural numbers less than 1500 which are not divisible by 2, 3 and 5. Let's say I want to find how many positive integers less than equal to 1500 are such that they are not divisible by 2, 3 and 5. So how do we go about that? If you notice, 1500 is composed of only three types of prime numbers, 2, 3 and 5, right? There's no other prime number which is there present in 1500. If that is the case, this problem boils down to nothing but finding the phi of 1500. Why? Because phi of 1500 is the number of coprimes less than equal to 1500 and coprime to 1500. So all those numbers which will not be divisible by the prime factors of 1500 will be the numbers in contention. So that's why I will take phi of 1500. And what's that? 1500 into 1 minus 1 by 2 into 1 minus 1 by 3 into 1 minus 1 by 5. So this is nothing but 1500 into half into 2 by 3 into 4 by 5. So this is cancelled out. 100. This is 400. So there are 400 numbers less than equal to 1500. which are not divisible by 2, 3 and 5, right? Now what if I tweaked it a little bit and said how many numbers less than equal to 1500 are not divisible by 2 and 5? Let's say I remove 3 from here and I talk only about divisibility with 2 and 5. So how many numbers less than equal to 1500 positive integers are not divisible by 2 and 5? So nothing to get worried about here. Just it will take a logical extension of the previous question we have done. Just take 1500 and instead of multiplying here with the entire of this expression, just remove 1 minus 1 by 3 from here. So just do 1500 into 1 minus 1 by 2 into 1 minus 1 by 5, right? Just take out this 1 minus 1 by 3 component out of it, out of the picture. Why? Because we are not asking for divisibility with 3 here. Just remember this expression here is not the phi of 1500. It's not the phi of 1500. However, this is something that we can directly write. This is just an extension of this phi. So I can directly write this expression, and this will give me 1500 into half into 4 by 5, which is nothing but 600. So there are 1600 integers less than equal to 1500 which are not divisible by 2 and 5. So even if I didn't calculate the phi of 1500 here, but I can find the divisors, the number of numbers which are not divisible by 2 and 5. All I am doing here is taking out all the numbers from contention which were divisible by 2 and 5, and here also I did the same thing. I was taking out all the numbers away from contention which were divisible by 2, 3 and 5. So this should give you some idea. Let me take another example of a slightly little bit more tricky. So let's say I'm trying to find all the number of positive integers less than equal to, let's say, less than equal to 400 which are not divisible by 2, 3 and 5, which are not divisible by 2, 3 and 5. So what's the tricky part here? The tricky part here is 3 is not a prime factor of 400. 3 is not a prime factor of 400. In the earlier examples we saw that the 2, 3 and 5 all were prime factors of 1500. Here 3 is not the prime factor of 400. So how do we go about that? We cannot directly apply Euler's Totient function of 400. So now let's do one thing. Let's see what's the multiple of 2, 3 and 5. It's 30. So LCM is 30. So now let me choose a number which is the closest multiple of 30 to 400. What is that number? It's 390. 420 is a bit farther away, so let's take 390, which is more closer to 400. Now since 390 is divisible by 2, 3 and 5 each of these, because I have taken it to be a multiple of 30, so obviously if I try to find out all the numbers which are not divisible by 2, 3 and 5, obviously 390 is composed of other prime factors as well, like 13, etc. 2, 3, 5 and 13. But we are not interested in 13. We are only talking about divisibility with 2, 3 and 5. So if I were to find all the numbers less than equal to 390 which are not divisible by 2, 3 and 5, just extending from the last problem that we discussed, we will multiply it by 1 minus 1 by 2. I am excluding all the divisors, all the numbers which are not divisible by 2. I am excluding all the numbers which are not divisible by 3. I am excluding all the numbers which are I am excluding all the numbers which are divisible by 2. I am excluding all the numbers which are divisible by 3, and I am excluding all the numbers which are divisible by 5. So ultimately this is the total number of numbers less than equal to 390 which are not divisible by 2, 3 and 5. So understand that this is not exactly the phi of 390, but this is only a tool to calculate the number of numbers which is less than equal to 390 and not divisible by certain set of other numbers like 2, 3 and 5. So what is this value? 390 into half into 2 by 3 into 4 by 5. So this is 104. So I am saying that up to 390 there are 104 numbers that are not divisible by 2, 3 and 5. But my original question asked me to find what are the numbers less than equal to 400. So if I see this range between 390 to 400, I'm sure there will be extra few numbers which will not be divisible by 2, 3 and 5, and we'll have to take them into account because till now we have only found till 390. So remember, before seeing all those numbers between 390 and 400, I understand that those numbers cannot be a multiple of 2. So let's exclude the even numbers. Those numbers can also not be a multiple of 5. So let's exclude those type of numbers as well. And let's see which all numbers are not divisible by 3. Let me write them down first. 391 can be 393, 395 we have excluded already, 397, 399, right? Now out of these, let's see which are all the multiple of 3. 393 one is obviously a multiple of 3, so let's take it out. 399 as well is a multiple of 3, so let's take it out. 397 is fine, it's not a multiple of 3, so it's fine. 391 is also not a multiple of 3, so this is also fine. So we get 2 additional numbers in the range of 390 to 400 which are not divisible by 2, 3 and 5. So if I add 2 to the number 104, I get the total number of numbers, which is 106, which are less than equal to 400 and not divisible by 2, 3 and 5. Hope this video cleared your concept on the Euler totient function and gave you good insight into the problems that can be used or tackled by using this tool. Thanks a lot.